this video will lead us through some sample problems to just help increase your confidence with molarity, molality, percent composition, and when you're making dilutions. So to solve these, what I would have readily available, I like to have an equation sheet. Then I don't have to search out for our different equations. I would have a periodic table and a calculator. Now, if you want, you could pause and just solve these problems on your own and then compare your answers with mine at the end of the video. Do not do number 5. Number 5 involves colligative properties. That will be our focus next week. I'm going to walk us through each one. Speed me up if you want to jump around, but I'm really illustrating, the thinking that we should be having as we're attacking these different problems. So let's just solve kind of one at a time. So ladies and gentlemen, what I would do first is make sure I can identify which solution concentration expression. So this first one, I see a lowercase m. Now, a capital M will be molarity. So the term molarity, a capital M, it also could reference a solution as being, for example, 0.100 molar. And sometimes it's a capital M just to help us make sure that we're referencing molarity. Molality, that's our lowercase m. And of course, we know the difference. They both, molarity and molality, are per mole of solute, but molarity is per liter of solution, molality per kilogram of solvent. Now, you'll either see the lowercase m, excuse me, or you'll read molality, or it could say that you're dealing with a 0.52 molal potassium chloride solution. So, molality, molal could be utilized to also be referencing molality. Percent comp, we've had some experience with that. Now, dilution. How do you know when to use this equation? When you are asked to find a lower concentration or to make a lower concentration, and you also are given the solution with the same solute, but you're also given the concentration that's higher. So the higher concentration will be your stock solution. So it's the same solute that you're either trying to make a lower concentration of, or trying to find out what the original concentration was that led to the lower concentration. So the key is you're reading the same solute in the problem, but you're dealing with two different concentrations of that same solute. Then we know we're implementing this equation. Okay, so to dig into some problems. All right, first. Okay, determine the mass of barium nitrate contained in, lowercase m, my molality. Now, determine the mass of barium nitrate. So is that my solute? Well, usually we're dealing with water as our solvent. Not always, but a lot of the time. So especially when it says made with this amount of water, then we know waters are solvent. So I'm going to write down my givens. So I have the mass of my solvent and the molality. Now we know that molality can be expressed as a conversion factor. And what we're doing, of course, is just expanding what we know molality to be. Molality is mole of solute per kilogram of solvent. My solvent is water. There's my solute. So I can actually use that as a conversion factor. I have two givens. I would favor starting with the simpler given, and then always keeping in mind what you're trying to find as your final answer. If you make a misstep, you just start again. All right, so I'm going to start my problem with the 250 grams of water. So I'm starting in perspective of my solvent, and I want to end with mass of solute. Now, let the problem guide you. I know I don't want grams of water as my final answer. Okay, so where do we go from there? Well, again, I'm in perspective of my solvent. If I look at my other given, here's my solvent, but it's in kilograms. So if I would convert from grams to kilograms, then I've canceled out of grams and I can directly use my molality as a conversion. Check this out. Now I'm in terms of mole of my solute. Da-da! And we know if we have moles, we just get the formula mass from the periodic table. So 1 mole of barium nitrate. And so I want to be careful. I'm, of course, adding up 6 oxygen plus 2 nitrogen plus 1 of my bariums. And I get a formula mass of 261.32 grams. And then doing my math, okay, so my answer, I'm going to really quick double check. Now 5 sig figs, 3, 4. So this is limiting me to 3. 52.3 grams of barium nitrate, but I'm going to double check. I always like to do my math twice because it's so easy to make a misstep in your calculator. And yep, there's our answer. And that's reasonable. Given that amount of solvent and that molality, that definitely is a reasonable answer. So there's number 1 for us. Okay, now let's go to number 2. Just get some more paper. All right, so I'll go ahead and log my answer. So if you want at the end to just go back and check the answers, they'll be here. Okay, describe how you would create 2.50 liters of 0.800 capital M, that's molarity, from 1, okay. So here's where we have the same solute. So this is what I'm trying to make. So because I'm trying to make it, I'm going to go ahead and use my dilution equation, of course, but I'm going to call what I want to make my second. So I'm trying to make this volume of this concentration from this initial concentration. So I'm looking for V1. Now describe how you would create, that's our recipe. Okay, so M1V1 equals M2V2. I will just rearrange the equation here. Looking for V1, so dividing both sides by M1. I'm just going to plug and chug. So 0.800 molar magnesium hydroxide, and I want 2.50 liters, and my higher concentration is 1 molar. Whoop. All right, and the answer that I got we have and 2. Now, your units of molarity of your solute cancel. So this will be liter. But liter of what? Well, what I found was my V1, which is referring to the 1 molar magnesium hydroxide. Now, if I would just take a grad cylinder and measure out 2 liters of 1 molar magnesium hydroxide, have I made what I was shooting for? Well, the 1 molar won't become 0.8 molar until I add solvent. So the amount of solvent, remember, will be the volume of the solution that you're shooting for minus the volume of your stock. So this is your solution volume 2 minus the solution volume 1, well, that's the difference in volume will be the solvent that you have to add. So, of course, now when we subtract, we respect least precise decimal place. So 0.50 liters of solvent, which I think we can go ahead and assume is water, but if we want to be extra safe, we would say plus 0.50 liters of water. And that is the description. So you're giving the recipe, if you will. You need to measure 2 liters of which solution, your stock, and you're adding that volume of water or your solvent. Okay, and that is the answer to 2. So we would take 2 liters of the 1 molar magnesium hydroxide plus 0.50 liters of solvent. Oh, number 3 is also colligative property. All right, so let's jump right to 4. And number 4, dealing with percent comp. Okay, so what is the percent by mass made by adding this solute to that amount of water? Now, percent by mass is mass of solute per mass of solution. So I'm given my mass of my solute. But what will be my mass of solvent that I add to the solute? Well, usually, because water's a liquid, we measure it in terms of milliliters. But milliliters would not go here. Now, we always have to be careful making the assumption, but we have to here. We need to move forward trusting that we can use the known density of water, which is 1 gram per milliliter. And so for the 15 mils, it'll be 15 grams of water. Now, that's not perfect, and it's not always 1, but otherwise, how would we solve this? So we must have to make that assumption. And it's okay if you don't do the factor labeling here. We are ending up with the mass of solute per mass of solution. So then I take my 1.50 divided out by my 1.50 plus the 15.0 times 100. And we will report to 3 sig figs, which would be 9.09% of the potassium bicarbonate. Okay. And we want to make sure that we are identifying the solute, the solution by the solute. Okay, ladies and gentlemen, so one more to walk through with this set of examples. So if we look at number 6, determine the volume of a 0.5 molar lithium phosphate. Okay, determine the volume in milliliters of a 0.5 molar lithium phosphate solution that is required to react with 200 milliliters of 0.1 molar calcium nitrate. Okay, so what are we doing here? We're doing a reaction. We're going to have to do, I guess, what we would diagnose as stoichiometry. So for those of you that have missed it, it never goes away. So for stoich, we first need a balanced, correct chemical reaction. We are adding compound to compound. So double replacement. It's not one of our special composition. So our lithium will be paired with nitrate, +1 -1, and our calcium will be paired with phosphate. But our calcium is +2, phosphate's -3, so Ca3, PO4, 2. And then to balance, we would need a 3, move my addition, and a 3. Oh, I believe I'm mistaken. I think we need a 6 here, and a 2. So 6 lithium, 6 lithium, 2 phosphate, 2 phosphate, 3 calcium, 3 calcium, 6 nitrate, 6 nitrate. Fantastic. Now, you would not have to do phase symbols. We're going to learn very soon all nitrate compounds are soluble and calcium phosphate is insoluble. So this is a precipitation reaction. That's getting a little down the road. You wouldn't have to do phase symbols. Just get the balance equation. Okay, we need the balance equation for our mole ratios. You want to find your answer about this. So I'm going to start with the calcium nitrate solution. I'm given volume, molarity. We know we can rewrite this as a conversion factor. So I'm going to expand that out. And molarity is mole per liter of solution. This is my volume of solution. I want to find the volume of this solution, and we know we can expand this as a conversion factor as well. Per 1 liter of that solution. Okay, because I want to find the answer in terms of this, I'm going to start in perspective of this. And I have 2 givens. I'm going to start with my least complicated given. So, given 200 milliliters of the calcium nitrate solution, and you could put AQ, but I'll go ahead and put solution there. All right, let the problem guide you. I do not want to be in terms of milliliters. So I'm going to cancel that first. Well, if I look at my other given, it is involving liter. So let me get myself to liter of solution. Now I know my sig figs here are not going to limit. Okay, now I've canceled mils. Now I'm in liter of the calcium nitrate. Well, I know for every 1 liter of that solution, it will deliver 0.100 moles of my calcium nitrate. Okay, now that I'm in moles, now I can go to the mole ratio of the reaction. And I determined that for every 3 moles of the calcium nitrate, it will need 2 moles of lithium phosphate to react. Okay, now I'm in terms of what I'm trying to find the answer of. But now I'll have moles of lithium phosphate. And I want to be in terms of the solution that delivers it. So my next step will be to cancel moles of lithium phosphate. Okay, well, what has moles but the molarity? And I know for every 0.500 moles, I'll have a liter of that solution. Now remember, as long as it is a true relationship, it doesn't matter if the mole is on top and the liter is on bottom, or vice versa. You are interpreting a true fact that you were given in the problem. I just want to rewrite that so it's nice and clear. 0.500. There we go. Okay, so that will cancel moles of lithium phosphate, and I'm almost there. I don't want my answer to be in liters. I want my answer to be in milliliters. Okay, so just take and do the math now. So however you do this in your calculator. Okay, and I want to double check, but the answer that I get is 26 let's check sig figs, 334, so I can report 3. So 26.7 milliliters of the lithium phosphate solution. Now, is that reasonable? Okay, wow, I'm reacting 200 mils of the calcium nitrate. But look at its concentration, 0.1. This is 5 times more concentrated. So even though we have not a 1-to-1 mole ratio, that definitely is a reasonable answer. but I'm going to double check my math just so quickly. And I got the same answer. Okay, so let me write this here. Now, how do we know that this did not require the M1V1 equals M2V2? Because you're dealing with two different compounds, and it's a reaction. We're not making a dilution. So we need to approach it from this manner. Okay, ladies and gentlemen, here are our different sample problems with their answers. If you have any concerns or questions, please email your teacher. Thank you.